Thanks for having me. My name is Jason MacDonald. I'm with the Grid Integration Group at Lawrence Berkeley National Lab. I'll be talking about a vehicle-to-grid pilot project at the Los Angeles Air Force Base. The DoD is attempting to electrify their non-tactical vehicle fleet, and so this is the first, LA Air Force Base is the first place that they're doing that. The outline here, I'm going to do a short introduction, or hopefully short, and some system architecture, talk about a sample optimization that we're doing, and some integration challenges, and then I'll conclude with project status, as this is an ongoing project. It's been going for a while, but we don't have a whole lot of results as of yet. So the LA Air Force Base is actually just an office park. There's no runway. It's no vehicle or planes or anything like that. But it does have 41 mixed-use vehicles that move things to and fro on campus and take people off-site. And they're going to electrify all of those vehicles. And each one will have its own dedicated charging station. And what we're trying to do, or what DoD's goal is, to show that we can achieve cost parity by providing grid services with a conventional vehicle fleet, or at least show the direction that we could get to cost parity at some point in the future. LBNL was awarded an ESTCP grant to develop a software management platform that's supposed to handle fleet operations, optimally charge the vehicles, and optimally participate in California Ancillary Services markets. So in that, we've got a fleet management platform, charging and grid services optimizations, real-time charging control of the vehicles, and communication to and from them. And then there's a grid operator systems integration and communication. Our team is rather large. We're working with some folks on UC Berkeley who recently joined us to help us with real-time charging control. LBNL is involved in the optimization and the real-time charging control aspects. We have Honeywell's Akuacom doing grid communications using OpenADR, and Bosch is providing fleet management software and doing charging communication software. So the primary objective, as I said, was to move from conventional vehicles to electric vehicles. And to do that, we have to manage the PV fleet's dispatch and charging, ensure that there's always sufficient charge for everything that the vehicles need to do, and charge these PV fleets in a cost-minimizing way under a retail tariff for electricity while providing wholesale grid services, and optimize that participation in those wholesale grid services to really determine the extent to which PVs can meet or get close to the same cost as conventional vehicles. The highest value services we find, grid services we find in the wholesale market. And it was a DoD directive to try to get these vehicles under providing regulation, both regulation up and regulation down. The wholesale market, of course, is the California ISO, and in the CAISO, prices or historical prices suggest that we could potentially be making about $8.4 per kilowatt a month. It's something comparable to some DR programs, which for a Nissan Leaf could be about $88 a month, considering the size. And actually, a fair portion of our vehicles will be Nissan Leafs. So to explain ancillary services, I probably don't need to go into too much detail for this crowd, but we have operating reserves. They're somewhat larger, deeper discharge events, up to 7% of the system load. The operating reserves respond to provide their full reserve capacity within 10 minutes, and an event duration is typically 10 to 30 minutes. They're rarely used, and it's always used for things like transmission outages or generator outages. And then we have regulation, which is what we'll be doing in this project. And this is trying to rectify the differences between load and the 5-minute real-time dispatch of supply. And something that a resource that's providing regulation reserve is receiving an operating point instruction every 4 seconds and moving along that instruction in the next 4 seconds. Theoretically, this should be an energy neutral if you have a symmetric up and down bid, but in reality tends to not be. So how we limited it with the PEVs and what we can use for regulation capacity, and what is it? Our regulation down capacity is actually, for reference, a charging capacity, the maximum charge rate being what limits you, or the amount of energy you can supply in your battery. And the regulation up is discharging, and we will have bidirectional capability with these vehicles, both charging and discharging the batteries. In our case, we're trying to optimally schedule charging as well, and we want to make sure that the ISO knows, so we'll be letting the ISO know when we're charging our batteries, which can potentially increase how much capacity we have for regulation up, and it decreases our regulation down capacity. So here's our architecture, or the start of it. My colleague who has left, Nicholas DeForest, he's seen this slide, obviously, because he created it, made a really nice, simple to understand drawing of it. So it starts with the dispatcher telling us when vehicles will need to be used, and that information is stored in e-mobility and passed to the optimizer, which is DERCAM, a Distributed Energy Resources Customer Adoption Model, a software platform developed up at LBNL for optimization of microgrids and been adapted for this. And then the charging instructions corresponding to with optimally charging or discharging in some cases, PEVs would go to the EVSE. Now, if we want to add regulation, all of a sudden we need some way to communicate with the outside world, which is our demand response automation server. The regulation bids will be a result of optimization. So the amount of capacity we're able to provide from the fleet comes from DERCAM and is passed up to the DRAS, which then passes it through a scheduling coordinator and turns it into a bid, which is placed in the ISO's market, and then we get awards back through, and any re-optimization that needs to happen can occur. In real time, we'll be receiving AGC signals directly from the ISO through our DRAS, and then into e-mobility, which is where the real-time charging control will be housed, or sort of, and we'll also be sending back 5-minute meter readings for settlement purposes. The optimization uses DERCAM uses a number of inputs. These are graphical representations of them. Here I've just got a sample fleet of 18 vehicles. And the colored portions are when the vehicle is not plugged in, and the intensity of the color shows how much energy it's using while it's not plugged in. We're under a retail tariff for electricity, which means that we have often mid and on-peak time of use rates, and we have demand charges, so the base load is important as well. And then we also need to know or have a guess at what the price of ancillary services will be to do the optimization. And then what we end up with is charging profiles individually by vehicle. And you'll notice here that all the charging tends to be happening at the end of the off-peak period, or most of it. And some is happening throughout the day to maintain enough power in the battery to provide regulation bids, because regulation turns out to be fairly lucrative. It also, we were keeping track of the expected energy in the optimization, the expected energy in total in the batteries, and that's represented here as state of charge, although it's energy. And that falls predictably while vehicles leave, and they come back a little less empty. When the vehicles are gone, you can't participate in the market. So you're seeing here that regulation up bids are, which was the more lucrative of the two most of the time, Regulation up bids tend to be higher than regulation down bids, and there's whole periods of the day where, because of constraints placed by ISO rules, there's periods where you wouldn't choose to bid at all because it would make further bids smaller throughout the day. So there are times when, because of the energy limits on the battery, you would choose not to bid. Additionally, our integration challenges are really the whole business environment has been a challenge for us. This is a really simple explanation of the physical layer of the grid, generation to transmission to distribution to our electricity load. We have 2 meters on the base. We have a meter for retail and a meter for the ISO. Now, the ISO is running transmission, whereas we have to get access to the ISO systems and the ISO market through the distribution system. And the green arrows trying to indicate dollars, how dollars move. In a typical situation where you're just buying load, you buy at retail, your retail provider, the investor-owned utility, would be buying from the wholesale market on your behalf, and then the generator would be getting paid through a scheduling coordinator. Now, what we're trying to do now is we have to add in a scheduling coordinator because everyone who is in the ISO needs somebody to represent them, and we need that. Unfortunately, that has to be the IOU. So the IOU has been asked to do something that they don't usually do on our behalf. And so for the IOU to do anything, you need to get the involvement of the regulators. So because they don't necessarily see profit on it, and they need to they need to be able to recoup their costs. So we have to get regulatory involvement as well. So all of these parties have been involved in this project at some point or another, and are ongoing, still involved. And this has been major challenges because there really isn't any precedent at all. We're doing a financially binding pilot, and so there's no precedent for this type of resource in any of their systems. So we're breaking ground on every front. The IOU does not have. I mean, they act as a scheduling coordinator for their own resources, but they've never had to bill anybody else for that service. So then they have to come up with systems for that, and there really isn't a whole lot of incentive, at least in the current tariffs and things, for them to even want to do this. So that has ended up delaying the project a little bit, among other things. There's also, the electric vehicles are really not the same as a typical grid resource. Your typical grid resource is solely dedicated to grid activities. It very rarely changes in size. It has few energy constraints, although now we're getting batteries and stuff on the system which are more constrained, and CAISO and others are capable of handling that. But they are always fixed locations. Electric vehicles the grid activities are really secondary. Mobility is the primary objective of an electric vehicle fleet. So allowing for that mobility and taking into account the energy consumed while providing that is a challenge for the grid resource, or for the grid operator. The size also changes daily. Our vehicles are coming and going, and we're bidding according to what's coming and going, but it's hard to convey that information to a grid operator. And then they're very energy constrained because of the secondary objective, and they can connect. In other vehicle fleets, they could connect anywhere. Of course, that's not an issue for us because they're all connecting on the base, all getting charged there. But so with CAISO, right now, their market optimization can't account for the missing vehicles and energy consumed while driving, which can limit awards. And we have engaged CAISO on this, and they're trying to come up with solutions with us, working with us on that. And then providing regulation also in CAISO is a challenge, in that we don't have a very good idea of how often the vehicles will be used and what the depth of will be used. And it's not there's a lot of risk to the state of charge of the battery. How much energy will be lost while providing regulation, and that's not clear even with what little data that we can get from other sources. status, our concluding remarks. So right now, we've managed to get charging and bidding optimization complete. Our grid communications are almost done. Fleet management and communications between system components is complete as well. And we've had some integration challenges, but we've worked through most of them, and are still getting through a few others. The first vehicles, it's starting to become an exciting time. We haven't had vehicles on the base yet. The first vehicles are scheduled to arrive hopefully this month, maybe a little bit later as things progress. And right now we're still working on the charge and control algorithms and real-time communications to vehicles. We are integrating, one thing I didn't mention is we're integrating multiple vehicles and multiple EVSEs, so each one of those has its own integration effort that is required. We're further along with some than others. And then we've still got to develop finish developing our forecasting tools and hopefully do some analysis of uncertainty in when vehicles will actually arrive versus when they're scheduled to arrive or depart, and how much energy will be left in the vehicles, and how much energy will be used while providing regulation. A lot of sources of uncertainty for an optimization that right now is pretty much not accounting for any of it. With some safety factors is how we're doing it so far. And hopefully, if everything goes well, our demonstration will be live finally in March of 2014. We'll be collecting data until, I think, September or November. And that's it for me. So any questions? Yeah. In the back, I think your hand up was first.
Oh, okay. From the research you've done so far, what type of demand response programs do you think are most compatible with electric vehicles? I mean, would it be like peak day pricing or capacity bidding or this type of program, do you think?
I'm going to be shooting in the dark. Right now we are doing a project with PG&E on something similar, looking at how electric vehicles, how appropriate they are for some of the demand response programs they have. My gut, commercial vehicles in that case, but my gut is that in most cases, demand response isn't really necessarily the best, or the typical demand response program, peak day pricing, things like, or peak day pricing I suppose could work, but just interruptible peak type demand response wouldn't be the most appropriate, because if someone's charging at that time, it's because they need to charge to get home or something like that. So I think that these sort of reserve products that are all day long, ancillary services, might actually show a lot of promise for electric vehicles for that reason.
I was wondering, I want to dig in on something you said when you were talking about the optimization algorithm, that it tends to do all the charging right at the end of the off-peak period. And I'm wondering, I'm wondering why that is, and I'm guessing it's because it's trying to maintain room to reg down overnight? Or?
Yeah, although that would be my assumption.
Okay.
But if you look at the results, it is providing reg down overnight and doesn't really care in the middle of the day. But it's not necessarily greater than upregulation, which makes me think that it's still leaving more in the battery than it needs to. Because you could potentially be leaving a lot less in the battery. It might just be a function of the amount of energy consumed in the vehicles throughout the day, and there's just not that much. But I don't know. I would expect to see higher down reg than up reg if that were absolutely the case. So I'm not entirely sure. But what you can say for charging right before the end of the off-peak is it charges then because, obviously because that's the cheapest time to charge, but also where you want to be with when you're providing regulation is right at the middle of your state of charge. And so if you have trips or intending trips that would require more than half of your range, then there's no reason to charge until you absolutely have to. So that'd probably be the reason I think that it's doing what it is.
So quick follow on. So are there any concerns about it sort of all stacking up at the same time in that way, or is the overall magnitude?
You mean from
either from the base or from the ISO?
So I show on this, you got your base loading on the second one down on the left side there. You have your base load in gray, and then you've got a little tiny green for your peak or your PEV load.
Oh, I see.
And so it's not actually, and this is only 18 vehicles, and we're going to have 41, and some of them will be bigger than the vehicles shown here. But it's a 4 megawatt peak plant, and I didn't say this, but we're trying to get to a 500 kilowatt range for the size of the vehicles. Because that's the minimum to be a part of CAISO. So we, and in this case, the charging, part of the reason why charging is pushed out is because it actually, even though it might look like you're creating a new peak, you're not. It doesn't create a new peak in this situation there, because it's just kind of a flat valley. The peak is a little later.
Okay, thanks.
Yeah.
Have you been directly involved in developing the user interface that allows drivers to choose their parameters and set points? In other words, say, for example, I'm a user, and I want to specify my target SOC, and then at the time that we transition into this off-peak or this peak duration or interval, I have a target SOC that's not 100% or even 80%. Is that something that's been...
So the way that I think our system, and Bosch is actually providing all the user input, Bosch's e-mobility suite is where the dispatchers enter in all their information. But we don't specify, or the user doesn't specify what they want their charge to be at. They specify trip distance and things like that. And we take a conservative estimate of how much they'll need to do that trip. Any others?